Soy otra vez Nicolás Lupi, director de Asosystem España. Pues bienvenido a este seminario online acerca del diseño y fabricación, del tema de moda, diseño y fabricación aditiva. Este seminario, la gran parte se va a hacer en inglés, aunque en la parte final va a durar más o menos 60 minutos, una hora de presentación por parte de los expertos de Dassault System en la materia. Y al final de la sesión contestamos a preguntas. Os invitamos a hacer las preguntas a través del sistema, escribiendo, y contestaremos a las preguntas verbalmente en la fase final de la sesión. Pues sin más, la agenda de esta sesión, lo que he dicho, 60 minutos de presentación y luego preguntas. Van a hablar dos personas. Va a hablar primero Juan Francisco Messier, responsable para Francia, África, Middle East, España, Portugal de la marca Katia en Dassault Systems, que va a presentar un poco la iniciativa global de diseño y fabricación aditiva, en la cual habéis podido ver rápidamente en la convocatoria que, bueno, tenemos acuerdo de colaboración con empresas como Airbus o Safran para desarrollar una herramienta adaptada a las necesidades del mercado. Y hablará Daniel Pisac desde Aix-en-Provence, cerca de Marsella, que hará una presentación técnica de las herramientas que conforman nuestro conjunto de productos, nuestra solución de diseño y fabricación aditiva. ¿Vale? Último comentario, los que están interesados, organizaremos más webinars más adelante, ya que nos preocupa desde Dassault System, bueno, seguir en la última de las tendencias del mercado, de la industria, y un seminario que organizaremos en las semanas próximas será acerca de la continuidad digital en los procesos de ingeniería, industrialización y gestión de operaciones en el mundo industrial. ¿Vale? Pues os mandaremos información y espero que todo sea interesante. Lo que voy a hacer a continuación, voy a pasar la palabra a Jean-François Messier, que va a pasar como presentador y presentar la iniciativa antes de ver la presentación técnica. Jean-François, tienes el micro abierto. Tu as le microphone.
Do you see my screen? Do you see my screen?
Okay, now you are presenter.
Do you see my screen on the cloud? Okay.
It's coming. 1 second. Okay. You're on the floor.
Okay. Okay, that's fine. So first of all, buenos dias, Jean-François Mézières. Thank you very much for inviting us to present you. Let's say our solutions for addressing this new technology more and more implemented, which is additive manufacturing. So I will have the pleasure to present you the way we, Dassault System, do really approach this demand from our growing number of customers, whatever is industries, and the solutions that will be illustrated in a second phase in this presentation by Daniel Pisac. So first of all, we are effectively facing since, let's say, 5 years, a tremendous change, not only in materials, technologies, but the way we do address at the end customers, users' needs. The world is changing in order to finalize, customize at the product that could be originally in another way standardized. So this will be approached and aborted by different actors. The ones that will provide new materials, new fibers in terms of plastic, for example. The ones that will provide new services, engineering services. The one will produce new machines and productions, for in other words, new ecosystems. And it is definitively in these new ecosystems that Dassault System does plan to work a tremendous active role in providing to companies, whatever the company's industry is, whatever the size of company is, to really help them in serving their final customers. So as you have already seen, 3D printing or additive manufacturing is really diffusing in all industrial sectors. You do see here some illustrations, medical, industrial, final business to customers chain. And we do see here in different purpose for new housing in plastic, for example, in new design in studying, as well as AC architecture, where we do also host in Dassault campus complete, let's say, house that has been produced by 3D printing, definitively in the aerospace defense, where comes the need to reduce the weight, which is attached to additional cost. To maintain a product, it makes sense to consider those new technologies as an additional and serious option to meet those challenges. Example in the aerospace defense or printed parts in maintenance, repair and overhaul sectors. For ANSAT helicopters, they already produce those parts to repair the parts. But not only, just a smile to the Tour de France 2016, where a lot of participants did really leverage this new technology for their suite, for their bikes. So it's really diffusing a lot of sectors. I was yesterday in a 3D printing show in Lyon, where there were a lot of actors in this medicine prosthesis domain that are seeing in 3D printing technology a very strong opportunity to respond better to final clients, having lighter parts, easier to support, and for sure better to repair and install. But not only, the AC industry as well, for mock-up, for being able to have a look on a building, on a house, on a city, possibility to rapidly generate a plastic 3D printed part, and to really react to customer response demand in a minimum amount of time. We do also see a lot of plants, programs that are launched over the world, where here we do really speak about printing machine, a full plants. They will deliver 24 hours a day parts that will be either metal, either plastic, in order to support whatever is industries. So this trend is really massive over the world. We do also see the European Union that is really seeing in this printing additive manufacturing a huge digital economy transformation, helping the economy of all actors in Europe. But not only, you do have already in Spain Association Española de Rapid Manufacturing that has been put in place with a referencing site acern.net, as well as ADIMAT, I guess you are aware, that are really showing the strong, let's say, activity in Spain as well of additive manufacturing, without really forgetting to mention the first All Congress you did have in Barcelona in June this year. So all being said, there is definitively a momentum where all industrial sectors, for new product, for innovation, for maintenance, for repair and overhaul, for additional services in order to get new weighted reduced parts, do really show a strong interest in these manufacturing industries. So let's say how now Dassault, with a suite of product and 3D experience, are now proposing responses to those challenges. Last but not least, I guess you have understood, additive manufacturing is really embracing all sectors, all business profiles, architects, students, engineers, design entrepreneurs, show manufacturers, drone enthusiasts, whatever. So all industries, all sizes of industries are really impacted. And having this said, we do really distinguish, let's say, the industrial use case, on which we do plan to support you in metallic as well as plastic, but not only concrete as well, additive manufacturing technologies. And for this, we do illustrate for powder bed fusion, for example, or direct energy deposition, some solutions that will be presented in a minute, as well as material extrusion. So, as I did say, we do see this additive manufacturing as the kind of circular set of big actors. First of all, the silico material engineering, because we do speak first about material, whatever is metal, alloy, carbon, plastic, to really at a microscopic level being able to serve you in better managing the characterization of the material you're going to have in your printing machine and the mechanical properties you could expect from it. Second phase, which is what we're going to be demonstrated in a few minutes, the functional based design generative solution in order to give to the conceptors, designers in their hands a tool easy to use in order to develop and generate a first concept that will benefit of design optimization, that will follow some stress acceptable rules as well, and also being in a perceived material shape aspect acceptable for the final usage. So this second step is going to be presented in a few seconds, is the first brick of our offer that will be progressively put on the market. The third one is definitively addressing the production planning as well, the operations that will occur in a plant with different machines in order to handle, in case of line of printing machines, the cadence, the quality of your part, and also to be able to simulate the thermal stress that could occur from this manufacturing process. And because we do have also laser operation on the material, it's critical for us to be able to simulate these different capability of strategy you could have in running laser cutting operations or laser welding operations. And here as well, Dassault Systèmes does plan to offer you responses. And last but not least, number 4 and 5, it will be the, let's say on the 5, the additional manufacturing hub that will provide quite soon, enabling all the actors, machine providers, material providers, academics, research centers, engineering experts, machine builders, as well as manufacturing builders, all those contributors being able to be connected to each other and to benefit of services, whatever, to provide a printing operation, an assembly, an engineering optimization service operations, providing materials, powder, for example. So this community will facilitate the connections over the world of all industrial actors participating to these additive manufacturing activities. So just have a look on the Silico Material Engineering. Here's the purpose with BioVia brand of Dassault Systèmes portfolio is definitively to run a characterization of your powder of metal, of your fiber of plastic, in order to optimize the quality you would like to get at the end of this additive manufacturing process. So this is not yet part of the offer, it's already available, but this will be starting helping you to address the subject. Definitively the solutions that will be going to be presented to you will be aiming to provide you once again easy to use design solutions that will be based on a kind of scientific approach with FEA calculation and optimization that will be completely, let's say, transparent to the end user. So it's very important of taking care of the acceptation of the designers of such tool in order to acquire for him and use it in a very regular way. Let me show you one illustration of this fabrication additive manufacturing offer in a context of design car for innovation. I do guess you do see my screen. So here we are designers in a car component for a door opening system, and we do want to, let's say, produce this gray part in an additive manufacturing manner. So we are in the 3D experience platform of Dassault Systèmes, enabling to the designers to start on a very detailed, general, original concept to run first kind of a design. So we are on the first creation, where simply the designers will take the part in the assembly and will partition it in order to consider the areas of importance of the part, where it will define the way this part is linked to the exterior. So it will define its requirements in terms of boundary conditions. It will as well define the loads, boundary conditions that will apply on the part, the way the part will be connected to the exterior, in order to really take into account how this part is going to be used in the context of the assembly of the car. And then it will put an objective, for example, reducing the 25% of the mass of the final part. Then in a transparent manner, the computation will be run, where at the end, the end user designer will see the distribution of the density of the part and the way the part will be optimized. At the end, you will have a final proposal that will be validated from the original stress acceptation in terms of maximum stress, and will be able to ensure that it is fitting with the expectation. And final step will consist of redesigning some detailed part, benefiting of an integrated set of tools inside the offer to the end users, enabling to, from a perceived quality aspect, get acceptable surfaces on a final part. So this is the final phase of the offer we are now putting on the market, enabling from an original part to really optimize the final one in order to get weight reduced in an optimized way. So this is just, let's say, an appetizer where definitively you do see immediately the huge gain in terms of mass reduction that you can get from this approach. This is an example in the car industry. This can be definitively duplicated in other industries, and this will be with pleasure that Daniel Pizak now will illustrate to you how this solution is running. Daniel, up to you.
Okay, merci Jean-François. Now, Daniel, you can speak, and in a few seconds I will give you the control of the presentation. Okay, just a second. Yes. Okay. It's now loading your screen. Okay. The floor is yours.
Okay, thank you, Nicolas. So, as Jean-François stated earlier, there are 5 important topics to cover when we talk about additive manufacturing. I will come back to the first one, the fourth, and the fifth, but I will focus more on the second and the third in my next presentation. So let's start with the part aspect, the part design aspect. You know, I'm visiting a lot of customers everywhere in the world dealing with additive manufacturing, and most of them, when I meet them, they told me some of them are proud of themselves, some of them are not proud of themselves. But the one who are proud of themselves tell me, Daniel, you know, after 4 years of having experienced this new additive manufacturing machine printing a metal part, I can claim that my success rate is 75%. It means that 25% of the parts that they are 3D printing in metal have to be thrown away. What does it mean? It means that it is very, 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 and the key of this is coming by the knowledge of 3 important pillars: the material, the design, and the process. If you missed one of these, you will probably have much less than 75% of success. Okay, so let's start now with the second one, which is the design aspect. As maybe you are aware of that, but topology optimization, which is a finite element analysis technique to reduce the weight and the volume of a part, keeping its stiffness, is an old technology. It was on the market since maybe 20 years. But the shape that was proposed by the topology optimization tool were so complex that we could not manufacture them at a good cost. For sure, we could make some casting, we can make some injection molding, we can make some milling, but it was so complex shapes. You have to refer back to the previous videos that Jean-François showed you, that it was just stupid to make it to fabricate it like it is. And so we have to transform the part to have something more mechanical. Now, since maybe 5 or 6 years, there are some printers that can produce very effectively metal parts at a good cost. And those very, very organic and strange shapes can now be printed at a good cost. And so the emergence or the maturity of metal part machines bring a new renaissance to the topology optimization, because, and this will be shown in my demonstration, because now you can print at a good cost very, very optimized shape. It's not an interpretation which will lose some gains of the topology optimization. It's a real topology optimized shape, and you can print it a good way. But topology optimization is still today something very complex. You need some finite element analysis background. You need some guru expert in CAE, and typically the mechanical designers like I am, we do not understand them. We are not using the same language, and we are not talking to each other. So the idea is to take the best of both worlds, the expertise in CAE of the gurus and the mechanical good sense of designers, and to bring together those two worlds to make one single app or application that will combine that. And this is typically what we are delivering today in CATIA. It's called the Generative Design Explorer, and it's embed not only topology optimization, but also structural analysis and reconstruction of CAD model from the result of the topology optimization in a very, very simple way, easy to use, no data exchange, no data transfer, and it is for us the future of the design. After having doing CAD modeling and then solid modeling and then feature-based modeling, functional modeling, now we are doing really science-based design, where the system will propose to you a solution, and then as a designer you take your responsibility and you modify if you need this design to fit your specification. Let's have a look at how it works. So the best is to run a video, and I will stop at any time to explain to you the various stages of the videos. Okay, let's start. I'm a mechanical designer. I am in CATIA 3D Experience. This is my app CATIA, and I have in the app called Generative Design Explorer. In this app, I will have everything I need to perform structural analysis, a topology optimization, and a reconstruction of my CAD model to be either 3D printed or manufactured in a more conventional way, such as casting, injection, stamping, or milling. Okay, so let's start. The part we would like to redesign, thanks to the science-based design, is this part, which is in the middle of the screen. As you can see, it is fixed on a beam with 8 different bolts, and it is supporting a part, a heavy part, which is rotating. Okay, so let's start now the process. The very first stage of the design is to create in 3D the so-called design space. The design space can be seen as an allocated volume in space where my part, my future part, will be located inside. Okay, so here we could have used our solid modeling part design or our surface modeling generative shape design in CATIA. We decided to use a new app which is on the 3D Experience, which is called CATIA Natural Shape. As you see, it's a very, very simple tools, direct modeling, very simple to use. It can be used by FEA guys as well as, let's say, CATIA geeks, and but it creates an allocated space. This space could have been done, could have been given to you or to me by my boss, because this is a step file coming from whatever, or it is just the allocated space from an assembly that I have to deal and to create my part inside. And this is my space. Now I still am in the 3D Generative Design Explorer app, and I'm starting to prepare my specification. Okay, first, very important action, I have to assign a material to my part. Let's select this material. That's it. And now I will curve out, I will partition my space in subspaces. Typically, those subspaces that you can see here around this axle and around the bolts are areas where I would like not to remove material. I would like to keep some material around that. So, As you see, it's a very simple, straightforward user interface. You have a wizard with traffic light. When the traffic light is green, you go to the next step. And when all the traffic lights are green, you can launch the computation. So here I'm defining my functional areas, okay? If I want, I can at any time display the mesh because it's a finite element model here. Usually we don't do that at the beginning, we do that at the end if there is some tuning or refinement to perform to the analysis. Okay, my functional region are those. I click on them, very simple. And this one, we have 8 bolts, we have the axial areas. This is done. Now I will define my loads and my boundary condition. For the loads, it's very simple. Here it's a bearing load, so I select among the various available options bearing load. And I type in the force in X, in Y. So this is here in X. I type the force in Y. So I have 2 loads, and I will combine those loads, bearing load 1, bearing load 2, and I will create multiple cases. So I have the flexibility of combining those bearing loads in multiple options. Once the loads are defined, I can define the boundary condition. I could have clamped the part, could have taken the bottom face and say it is clamped. Here we are a little bit more precise. We will define the boundary condition as been done through fasteners. So I will define now my fastener boundary condition. I click and I select, as it is a bolt, the head diameter, the nut diameter, but also a stiffness both in translation and rotation. So those are easily done in the app, in the Generative Design Explorer app. The system is quite smart. He noticed that there are 1, 2, 3, 4, 7 different holes with the same diameter and the same depth. And he asked me, do you want to copy, to replicate this bolt fastening conditions to the other areas? I say yes, and automatically the definition has been replicated to the 7 other bolts. Once this is done, the next, find a target. What, Daniel, would you like to optimize? We have various options. We can optimize the stiffness, we can maximize the stiffness, minimize mass, maximize stiffness with an associated mass, and here I will decide to maximize stiffness and to reduce the volume. So I type in here a volume reduction. So let's be very ambitious, and I type a 6.5% volume as a result. So 93.5 target, a percent of volume target of reduction. This is done. And now I define some other constraints. You will see what type of constraints I can put in. Here, I don't want to have a maximum stress bigger than a given value inside my part. Okay, so I will type in this maximum stress. As I have fasteners that I purchase from a supplier, I will also indicate to the system some other characteristic of the bolt that I buy from the suppliers. So select the fastener and now refine the information. What are the type of information I can add? A maximum X shear, a maximum Y shear, and a maximum tension that I can put on the bolt. So let's type in those values. It's very simple, very straightforward. I'm guided. And this is it. Now I can also add some constraints on the final resulting shape that will be performed through the topology optimization and the structural analysis. What type of constraints can I put? Let's start with a very simple one. I don't want to have a thickness, a part which is too thin in some area. So I put a minimum thickness. Let's put 3 millimeters. I also want, even if the boundary condition and the loading condition are not symmetrical, I would like to get a symmetrical shape. So I just click in the session, in space, on the plane, in the CATIA session, and that's it. And now I will perform the topology optimization and perform the structural analysis. You will see that all the parameters that I type in are in the spectri here, and of course I can modify them at any time. So let's compute the shape. This, of course, is not instantaneous. It can take some time. In this particular case, it took 10 minutes on a laptop, on a normal laptop. It can take sometimes more than that. It can be faster. It's really depending on how many constraints you put, how small is the meshing, how big is the part, so how complex is the part. So there are various parameters that influence the final computation time. But when it is computing, you can, by the way, continue to use CATIA if you want. So this is the result of the computation. So both stress analysis and topology optimization. What you see on screen, what is blue is empty. What is red is plain. In between, you have various areas of different densities, okay? So the user now, as a mechanical designer, can put a threshold. Here, the threshold is at 0.5, and the threshold is distinguishing between plain and empty areas. Between 0 and 0.5, it will be considered as empty. Between 0.5 and 1, it will be considered as plain. So what you see here is not acceptable. Okay, yes, maybe my volume is reduced by 93.5%. My stiffness is maximized. Mechanical part. So as a mechanical designer, I take my responsibility and I move the threshold to make something acceptable. Here, it could be better. It is better, but as you see, you have orphan branches. It's not mechanical. I don't want, it does not mean anything, orphan branches. So I continue to move my cursor. Here's something better. It looks mechanical for me. It looks producible, manufacturable, and I have still a good residual volume, which is 13, almost 14%. Okay, it's not 6.5, but still it's a very good result. By the way, you can see that the system is telling me that 4 bolts are enough. I don't need 8 of them. Okay, which is good news. I'm winning money. So now, once this cursor is finalized, in one click only, just one click, generate shape. And here it's real time. I get a CATIA solid. It's a CATIA solid, exact solid, made of cylinders, made of planar areas, and for those which are very organic shape, we created subdivision surfaces thanks to our subdivision surface technology in CATIA. For those who are familiar with a product called Imagine and Shape, which was mainly made for industrial designers, stylists, we use this technology to create those surfaces, which are exact surfaces, C2 continuous, curvature continuous surfaces. Of course, you will see that they are a little bit rough, but this is a CATIA solid. You can make here, if you want, a fillet. You can, of course, delete those 4 bodies which are useless. You can create holes. You can print it. You can make a drawing. You can even mill it if you want. It's a very exact CATIA solid. You will see that it's not enough for what we want to do. We will modify it later, but it's a solid. There is no break in the numerical continuity. Most of the optimizer, not only ours, but other optimizers create a mesh as a result, maybe an STL file. It's not an exact solid. Here, it's an exact CATIA solid. Okay, as I transform my geometry, I went from the design space to a new geometry. I have to validate my shape. So I have nothing else to do than simulate, validate, no other pre-processing. I'm not forced to redo the pre-processing. I just simulate and to validate my shape. Here I display the von Mises stresses, so it looks okay to me. I can display the displacement. I can display any other outputs that I want to select. And this is very important. Very easily, a normal mechanical guy can define boundary condition, loading cases, design a design space, and create a shape which can be a proposal for its detailed design. Now that it is done, a very, very important point is that this tool also helps you to make various alternatives, variant. By just copy and pasting an actual study, which was my previous study, I can quickly create a clone of this study and now modify some of the parameters. Let's imagine this part will not be 3D printed, but milled or cast. I'm not as ambitious as before for the volume reduction. So I type in a smaller value or a bigger value. I might create now, as the part is casted, I will ask the system to compute a shape which has no undercut along the pulling direction, the molding direction, which is here Y, okay? And the system will prevent any undercut in the final shape. I compute the shape. Again, I get a result. So now I have two options, two variant design. I can, of course, make as many options that I want because I have time to make to study more alternatives. Here again, maybe I change an optimization target. For example, I can change some other conditions, and I can compute a shape. At the end, in my particular case, I have 8 different variants, and now I will select the one which is the most appropriated, either to my weight target or my production constraints. Again, a shape for which will be 3D printed should be different than a shape that will be manufactured with conventional manufacturing tools such as milling. So let's select all of them, and now we can see the geometry, the input, the output, my KPIs, the mass, the maximum von Mises stress and stuff like that. I can display all the variants together. And to help me, now I am switching to another app. So I'm no longer in the same app, which is Generative Design Explorer. I go to another app, which is called Simula Results Analytics. And this tool helps me with spider chart, but also by giving weight to the various criteria, I can make a quick choice of what is the best solution according to my needs. Let's select this one, and now we go further. Now the job is to refine the shape, because yes, you can print it. Yes, maybe you can mill it, but you will have some issue because it's not that easy to mill. So let's imagine that this will be 3D printed, but I would like to have a better quality here of the resulting surfaces. So let's refining the shape. As the part is symmetrical versus 2 planes, I just work on a quarter of the part. Here it is. And here, in my Generative Design Explorer, I have a lot of tools to complete this refinement step. One of them are based on the subdivision surfaces techniques. And here, by just creating and dropping lines on the data, I can create tubes all around my data, my solid, very easily. And those are very, very smooth tools, very, very smooth surfaces. And from the various branches that I'm designing, I can then later on blend them and continue my design and incorporate this design with the current cylinders, planars, and all other features that was inside my part. You can see here the blending operation, very easily done. And at the end, as I modify my geometry, I have to validate. For that particular example, I asked my colleague, the FEA guy, which is on the office, the desk just beside me, and ask him to complete and to validate what I did, and he will perform some more complex simulation. For example, in this case, he will make a buckling analysis to compute the eigenvalues, and so he's doing that by himself. So adding some other FEA analysis. He's checking and he tells me, Daniel, there are too much constraints in a given area. He will put a compression and please change the design. So as you can see here, it's a real collaboration. I was designing the part with a very basic but complete structural analysis. For extra analysis, I pass the model to my colleague. He performs simulation and he tells me what to do. So in this particular case, I will have to change. So I do my Generative Design Explorer. I modify my shape according to the recommendation of my colleague. And as I modify the shape very easily, I have to perform a validation to check if now it's okay from a buckling analysis point of view and eigenvalues point of view. Checking is done very easily. This can be done in Generative Design Explorer, and it's finished. As you So we could do very easily what we called a topology optimization. But sometimes after a topology optimization, you would like to go further. You would like also to optimize the overall dimensions of the part, maybe the dimension of those branches, maybe the height, maybe the width of the part, okay? The good news is that not only you can modify, like with a virtual clay modeling, the tubes, but you can also modify it with parameters. In this case, what Katia did automatically for you, when I was creating the tubes, by dragging some lines, the system automatically creates circles, and the center of the circle and the radius of the circle are parameters that I can modify. So not only I can push and pull on the surface, I can also change the radius, and the shape is modified accordingly. And I can change the position of the radius, and the shape is modified accordingly. Now I have parameters. I can now perform a parametric optimization. So I will tell the system, you can change this circle, you can change this circle, maybe you can change the position of this one, but not its radius, and so on and so on. So you can freeze some parameters and give some freedom to the system to perform the best value of the other parameters. So in this particular session, we'll now move to another app of our platform, which is called Similia Process Composer. We tell the system what is frozen, where is the freedom, and the system perform an optimization of the parameters, find the optimal set of parameters that will fulfill my specification in terms of thickness, maximum von Mises stress, and so on. Okay, that's the first step. So after a topology optimization, I can do a parametric optimization. Now, just to show you that we not only think 3D print, you know, there is a big aircraft manufacturer in Europe. His wish is to optimize 100% of the part of the plane. But he is very pragmatical. He says 95% of those parts will be manufactured with conventional means, okay? But only 5% will be 3D printed. It's still a big number, but we have also to take into account the 95% of the part which are optimized, but need to be reconstructed, need to be manufactured with conventional ways. It's why here, what is shown here is that from the output of the topology optimization, we can also create a shape which is not really an organic shape, which is more something more you might be more familiar with, like pad, fillet, draft, if the part needs to be molded or casted. And it's a traditional way of building the job. So we have also inside the same Generative Design Explorer solid modeling, surfacing modeling to perform this type of redesign. And of course, as we redesign something, we have to validate the shape to see if the specification, the structural analysis is okay, which is done here, and so on and so on. And at the very end, you can see, oh, I'm a little bit too fast. You can see the result. So this was the initial part. This is the design space. This is one proposal of organic shape that will be 3D printed, another one, and this is a part that can be milled. And from that, you can see here the various options. We have here the so-called buy-to-fly ratio, which is a number, a buzzword in the aerospace industry. Buy-to-fly ratio means if I have to create this particular part, I will probably buy maybe 15 kilos of titanium, and to get the final part. So the buy-to-fly ratio is 15 to 1. Now, if I have to take this part, I'm no longer needed a block of 15 kilos. I just maybe, yes, I do need 50 kilos blocks, sorry, but I have less material. So I have decreased the buy-to-fly ratio, but not that much. And of course, when we do 3D printed, you do not start from a block. You just consume the amount of the mass of material you need to produce the part because you are burning powder. And of course, the buy-to-fly ratio is much more better. And that's here for the first step of the presentation, which is science-based design, thanks to Katia, Generative Design Explorer. I hope it was clear enough. So let's see where. Oops. Just have to switch. Here we go. And now that I showed you how you can design optimized geometry from specification, boundary condition and loading cases. I will show you how we can now prepare the programming and how, more important, you can simulate the programming of the 3D printers. So that's important. This is just a small story, a true story, okay? This is a Cobra Shelby car. The car has been 3D printed. Most importantly, the chassis has been 3D printed. And the chassis has been 3D printed with this type of machine. It's a machine designed by a US company called Cincinnati. And it's not metal. It's a resin which is reinforced with short carbon fiber, but it can create very, very big parts. It's so-called BAM, Big Area Additive Manufacturing Machine. So you can see here how the machine is behaving. So the idea was to make the chassis of this car. And you see here the machine. And you will see how this machine is, in fact, burning the resin and laying out the resin layer after layer, okay? And in fact, the story of this machine is that the very first chassis that they developed, once the manufacturing was finished, the very first chassis, when they took it out, you can see here the various layers. Every layers, almost every layers delaminated, okay? So it was completely broken. You have layers everywhere, okay? And so the people from Cincinnati came to Dassault Systèmes in the US, where we are developing our finite element analysis suite of solutions. And we analyzed what was happening from a stress analysis, from a delamination analysis point of view, and we helped them to modify the parameters. So maybe the width of the layer, maybe the height of the layer, maybe the trajectory of the deposition of the layers, and the final part, and the second trial that they made, everything was okay. So what does it show? It shows that the process of additive manufacturing is very complex, and you need to master the process to reduce the failure rate, okay? And this is typically what we are doing at Dassault Systèmes. We introduce inside the programming of the machine, it's the simulation of the manufacturing process. Okay, I make a small break. According to ISO, the ISO standard, there are 7 different ways of producing thanks to additive manufacturing techniques. Okay, and we are very ambitious at Dassault Systèmes. We would like to develop a special app for almost all of them, except one which is not that important, but almost all of them would like to develop a dedicated app taking into account the constraints of the machine, taking into account the material which is used by the machine, to provide a solution that help the manufacturer of the part to reduce the risk of failure. So just an example. Oops, my mouse. I am inside my additive manufacturing shop floor. Here in this case, it's an assembly of the 3D experience, so it's more scenic, but it could be the case. I am in a so-called app called Delmia. This was an old name, but the new name is Delmia Powder Bed Fabrication, because the priorities in terms of delivering a dedicated solution is first powder bed, second projection of powder, and the third one is wire deposition. We are mainly focused today on metal machine, even if you will see some of the features which are developed can be also used for plastic or resin machines. Okay, so let's have a look. So I am in my shop floor. First things to do, I have to select my part. So the part can be searched in the database, or here I have the part directly on the table. So I add a part to my context. I check what is the material of this part. It's aluminum. Knowing that, I will select my powder in my shop floor. By clicking on the barrels, I can see the characteristic of the powder. As you know, if I'm using powder bed or if I'm using projection of powder, the material might be the same, titanium, aluminum, but the diameter of the spheres of the powder is different, is obviously different. So I have to select the right barrel, and the right powder. Once this is done, I will, of course, also at the same time select the machine. In this case, I'm selecting an SLM 280 machine. So I have the geometry of the machine. I have the constraints of the process. I have also other characteristics that the system will take into account when it will guide the user in programming the machine. Let's select a build tray. So I will select the build tray in my database. As you know, or you might not know, but when you have a tray which is supporting the creation of the part, sometimes you use the tray as a fixtures to perform finishing operation with machining, for example, or you cut the tray. You need to cut the part from the tray, and of course you then finish a little bit the tray, and the dimension of the tray might vary along the life. So it's why for us a tray is a PLM object. It has its own life cycle that you have to take into account. It's why here I'm looking for the tray, and I'm looking for the last variant or the last version of my tray. Obviously, the dimension of the tray are automatically selected to fit the machine because I have given the information of what machine I'm using. This is my tray. The system has various ways to optimize the position of the part on the tray, to minimize the areas to be supported. You remember, depending on the process, but today almost most of the process of additive manufacturing need what we call support for overhang areas. Typically here, this area has an angle which is almost 10 degrees or 20 degrees according to the printing direction, and we need to create support areas here. Okay. For here, of course, there is no support area because it's almost vertical. So we need to optimize the position of the part on the tray to minimize the support and also to minimize the height, because the printing time is depending on the height of the part on the tray. And of course, the finishing time is depending on where are the support. Today, as an average, it is considered that 50% of the price and the time spent to get a part from a 3D printing machine is coming from the finishing. So because removal of those support is extremely painful, especially if it's very hard material such as titanium, Inconel, or stainless steel. Okay, it's a little bit easier on aluminum, but even in aluminum it's not easy. So let's optimize the position of the part on the tray to minimize the support and the height. The system has multiple options. I will detail that to select the type of support you would like to have. In this particular case, it's very simple. I will select just conical supports, and it will create those support in every single area, which are in between 0 and 45 degrees along versus the printing direction, which is Z. Here is a proposal of the system, and at this stage, I don't know if you noticed, but I do not change the data of the representation of the model. This is the CATIA part here. And the system is creating features directly on the CATIA part. I'm not forced to create an STL file or some other format. We have no break in the numerical continuity here. Okay, this is extremely important. So I create my support, and now I can stop. Maybe I say, okay, I have my support, I have my geometry. I might now output an STL file or an AMF file, which is a new ISO standard for additive manufacturing geometry representation, or EMF type of format, but I will detail that later. And this will be consumed by software coming with my printing machine or directly by the machine, and the system will print the part. But our customer would like us to provide much more. So what is it? So we have now solution to slice the part and the support, but not only slice. Some machine, for example, like EOS, do not like the outer shape of the support and the part. They prefer slices. So we could do that. We could slice and then send the data as a CLI format to the EOS machine, but we can do much more. So we slice, but we also select among various strategies of lasing the one which is the most appropriated to our process. Here you can see there is contouring for every single plane. We create contouring of the sections, and maybe we create this type of back and forth lasing strategies. We can have different lasing strategy for the support, because remember, they will be removed anyway at the end, so they might not be as strong as the part itself, even if, especially in metal, the support not only support overhangs area, they also transfer heat. Like in foundry, you know, when you are making a foundry or casting, you try to put the hot spot out of the part, and you create some special geometry outside of the shade that will be removed later on. It's very similar with support. It's heat transfer and of course support hanging area, overhanging area, sorry. So here we have the laser pass. We know the power of the laser. We know the temperature of the chamber. And we send now this information to our finite element analysis software. To make it more simple to understand at the simulation level, we remove from the display the support, but of course the support has a very, very important role in a thermal role. Okay, so we do that on the support as well. Here it's just to light the display. So we send to the finite element analysis app the model, so the geometry. We send the laser pass, the complete laser pass. Can be big files, okay? Because remember, we have layers between 30 to 18 microns, depending on the process. So it's very, very small distance between every single plate. And we have a big tool pass, and we send this with the power of the laser at any time. And from that, the system will perform, thanks to our Simulia structural model creation app, we will perform thermal analysis. So I go there, I select my app, and I perform a thermal analysis. The thermal analysis will show me the temperature of the part being printed during the printing process. I might discover some issues at that level. And more important, not only he perform a thermal analysis, but he can also couple the mechanics and create and compute a thermomechanical analysis. And from this thermomechanical analysis, I can have an idea of the stress inside the part. And from this stress computation, I can predict the distortion. Okay. So here, what we will do, we will also use Process Composer to optimize the process to reduce the distortion. And here the idea was as a demo, just to show you how we can, for example, play on one of the parameters to do so. The parameter we selected for this demo is to change the orientation of the lasing path between consecutive layers. So we'll put an angle. For the first layer, it will be a given angle. For the second layer, we'll rotate by a given angle. Let's change by 45 degrees. So for first layer, we have this, and for the second one, we have 45 degrees rotation of the path, and so on and so on. Okay. So now we will recompute the analysis. So thermal analysis, residual stress, and now we can compare the two options without rotation on the right, with rotation by 45 degrees every single layer, and check what is the best solution. Okay. Typically, you can see that here we have a lot of distortion and a lot of stresses, which is less the case in this particular area. We can even imagine that we ask the system to really compute the best option, the best angle to minimize the distortion. And of course, the distortion might occur, but it should be controlled and within the specification of the part. So here, obviously, on the right, it's too much. On the left, it looks like acceptable. And as you can see, I can simulate what will happen during the process. I can have an idea of the distortion of the part once it is printed, and I can really reduce the risk of a failure on the machine. For those who are not familiar with the printing machine or printing process, if you take a part which is 100 millimeter high and a diameter of let's say 100 millimeter, it can take 100 hours to print. and if after 100 hours of printing you see that the part is not within the specification and then you have to throw it to the garbage, it's not good news. Okay, so it's very important to simulate as much as you can upfront, and this is exactly what we do. And more than that, we can also simulate the process to get now an idea of how much material we are consuming and what is the print time, because those are the two KPI. The cost of a printing process is really depending on those two parameters, how much material I'm using and how long will take the printing. Because as you know, a printing machine is quite expensive, at least so far. It's between 500,000 euro up to 1.5 million euros. And if you use it for 20 hours or 35 hours to do the same part, it's a choice. Okay, so it's important to understand that. Here we go. This is for this process. I'm almost finished. Just quickly to show you that we perform a display for the user, for him to understand where we need some support, so he can modify maybe the design, he can modify the position, or he can rely on our optimized computation of the position. He can also do nesting of multiple parts, because as you know, a good news with 3D printing, you can print at the same time multiple copies of the same part or different type of parts. For the process of support structure creation, you have various type of support that you can select from. So I will not go through everything, but just show you a quick video at the end how to do that. This is the part that we would like to print. The system check what are the areas, the zone where we need to do support. Of course, this is also depending on the machine itself. You can then select a given area and select the right or your preferred support definition, and the system will perform the support. You can then, I will go faster, you can then apply to other area a different type of support. You see it's inside the same environment, no data transfer. I just take the CATIA part and work directly on the CATIA part. Here I have some 3 types of support that you can see. And I can also have different support for the bottom. You see, in my case, I will select like a microstructure that I will use as a pattern to be created to support the bottom of the part. Remember that all those support will be removed anyway at the end. By the way, for those who are familiar with 3D printing, this is not a good choice, because here this area which are horizontal need also to be supported. So I would need to take another type of support. But anyway, that's for the demo. And at the end, I have my geometry with all the support that I can slice and where I can perform the pass programming of my laser. Finally, very important, you have various options to define this laser strategy. Typical cross-check or chess pattern. You can also have more pattern lasing pass more close to a CAM, computer machining pass. You can have various areas on the part where you can define different type of lasering strategy for the outer skin, the inner skin, or the core. And then once this is done, and of course once you type in the parameters of the power of the laser or the temperature of the cell, you can output that to the various machine that you would like to drive, either in their native format using their API or using more standard format. Typically here the goal is to really reduce the gap between the as design part and the as manufacture. Okay. Taking into account the material, the deposition pass, the build definition, the heat, and of course showing to the end user the distortion, the residual stress, and what has been altered in terms of properties. So our goal is really to optimize the orientation of the part, to do the topology optimization, both and also parametric optimization, to optimize the structure, and also to optimize the pass, to get the part in the best condition, in the best possible condition, and reduce the cost of printing. As standard format are concerned, Today we can output, you know, STL. This is very, very famous. But we also support in both, by the way, CATIA V5 and CATIA 3D Experience, the additive manufacturing format from the ISO standard. It's richer, it supports color, it supports material, and there is a new format called 3MF coming from a consortium led by Microsoft, but we belong to this consortium as well as other software vendors, but also as well as machine vendors. And this is a very, very quick changing format. Typically in 3MF now, we will very soon support lasing pass. Okay, so maybe 3MF will be the de facto standard format for passing information between the various bricks of this additive manufacturing process. And I just heard a couple of days ago that maybe AMF and 3MF will talk together and have a common format, richer than what is available today. So good news. So finally, we also help you, if you have multiple machines, to really manage your shop floor, your additive manufacturing shop floor. Remember, I told you 50% of the cost of an additive manufacturing part is coming from the finishing. So usually in additive manufacturing shop floor, you have also, not in the same room, but maybe beside, you have also a wire cut machine, because you will wire cut to remove the support. You will have machining machine, you will have sandblasting machine, you will have a lot of different machines, and the additive manufacturing machine is just a machine like the other, even if, as you can see, it's not only a new way of building part, it's also a new way of designing part. It's what, for Dassault Systèmes, it's not an evolution, it's a real revolution. It impacts everything, material definition, process definition, and design of the geometries. So here, thanks to our Apriso suite of solution, you can manage your shop floor, optimize the production, monitor the shop floor, like if you were monitoring your assembly line or assembly production floor in your facilities. So this is available today. And very, very soon, as we think it's an important topic, an emerging topic, we will put on the market before the year end a website. It's not software, it's just a website. You connect to this website. Maybe you design something with CATIA or Google SketchUp or whatever, and you can add in this website your data, your 3D data, and you will ask what type of color, what type of material you would be the 3D data to be printed, and we will put you in relation with members of this community. We can print the part for you, so depending of course on the material, and you will make some bidding, they will propose some quotes, and you will do the deal with one of this company, and they will print the part for you. We take the money, and once the part is shipped and you accepted the part, we pay the printer. And at the beginning, it will be just a B2C hub platform, but very, very soon this will be extended to be B2B. So as an industrial company, you can discuss or you can exchange with, of course, suppliers or printers or fab labs, but you can also discuss with powder provider, machine provider, consulting people, universities, to share experience, maybe to buy some incentives, and really it will be a big business platform that help and speed up the adoption of additive manufacturing techniques all over the world, because it's a worldwide initiative. So as you can see, Dassault Systèmes is extremely ambitious. We would like you to develop new material. So with our virtual lab, you will engineer new materials. You will certify existing material. You will really understand the behavior of the material being 3D printed. One characteristic of 3D printing is that we have to take into account, it's not like machining, we have to take into account the phase transformation. When you are sintering metal powder, the powder is solid, then it is melted, so it goes from solid to liquid, then it's cooling down, so it's going from liquid to solid. We have to master that. And today we are working with various people, various universities and labs to take into account those phase transformation, and we very, very soon will deliver a true simulation of what is happening to predict again the real behavior of the material inside the process, inside the machine for a given part, to reduce the failure rate. So very aggressive and strategy. The design is already, the design topic 2 is already available. Topic 3 for the programming and the simulation is due for November this year. Topic 4 is already available. Topic 5 is for the end of the year. And the topic 1 with dedicated characteristic of the material for 3D printing will come next year. Thank you very much for your attention. And if you have any question, you can also ask them in Spanish. And I think Nicolas will translate those questions to me. So you take the end over, Nicolas.
Ok, merci Daniel. Acabo de mandar por el chat un mensaje. Lo más fácil, ya que somos más de 80 personas conectados, lo más fácil es que si tenéis preguntas lo hagáis por el chat. Y las en castellano, si queréis, se lo paso a Daniel. Resumiendo un poco lo que dijo Daniel, que lo resumió perfectamente. Aquí vemos realmente un poco la fuerza de Asosystem mediante la 3D Experience Platform, que es la plataforma de colaboración al cual se conectan todas las aplicaciones que hemos visto: Katia, Simulia, Delmia. Detrás está toda la parte colaborativa, los workflows, los procesos que permiten realmente conseguir una colaboración transversal en la compañía y aproximándonos a lo que es la continuidad digital, desde la ingeniería, el equipo de cálculo, el equipo de industrialización que prepara la programación a las máquinas y la parte de gestión de operaciones que hemos tocado al final a través del hub y de Apriso que comentó Daniel. Pues no tengo preguntas, entonces lo que os invito a mandarlas ya rápidamente. En cualquier caso, todos que si sois clientes existentes os invito a hablar con vuestro contacto comercial habitual, que sea distribuidor o directamente con Dassault Systems, o cualquier pregunta adicional, pues os he puesto a través del chat también un correo electrónico donde podéis mandar consultas y ya lo remitiremos a las personas adecuadas. Entiendo que ha habido bastante interés. Hemos tenido 80 personas que nos han desconectado toda la sesión y entiendo que, bueno, hablaremos de este tema que realmente es una tendencia, un punto de no retorno en la forma de trabajar que tenemos en el futuro. Vale, pues espero un minuto a ver si aparece alguna pregunta. Sí, una pregunta. La leo en inglés. Is your application able to foresee thermal distortion for laser metal deposition or only for SLM? Specific question for you.
Can you hear me? Yeah, can you
yes.
hear me?
Yes.
Okay. Today we are supporting the laser sintering laser process for any type of machine doing sintering, which is in fact a melting powder. Okay, that's for today. We are talking to all the machine vendor. The very first one where we already made some tests and everything is fine and running is Renishaw in UK. But we are also talking with all the other players like AOS, like 3D System, like SLM. It was an example of an SLM. The next step will be to perform similar simulation for powder projection, machine like Trumpf, machine like Mazak, machine like Deckelmau, DMG Mori, machine like BIM. And the third one, which might come at the same time, by the way, because we have customer asking for that, it will be also wire deposition. So we have metallical wire, which is melted with a plasma torch or other devices, and we want also to perform the simulation on those the three type of technology. It's very important for us. Simulation of the process is key, because the price of it's so bad to send in the garbage bin a part which is not good. Okay, it's very expensive, so we have to simulate that. Of course, we'll not perform the simulation for all the materials at the very first day, but for the most important material. For example, titanium 6.4, maybe then Inconel, maybe then some other margin, but not all of them at the very first day.
Okay.
Is there any other question, Nicolas?
Yeah, I sent to our internal chat another question. The question is, can we consider properties of deposited material as isotropic? Do different simulations consider them as isotropic?
As you know, it's a good question. As you know, 3D printing, for most of the machine, except the carbon 3D machine, which is a new machine, which is not yet on the market, which is, was flashing light, which is a very isotropic process. There is no step by step. Yes, for it's a non-isotropic process. Yes, we took into account this. Remember, we are relying on very strong technology. We are relying on Abacus, the nonlinear solver Abacus, where you can define isotropic and non-isotropic material. And we are also relying on an history of being able to simulate welding. We have a lot of customers worldwide using Abacus for welding simulation. And in one way, the simulation of additive manufacturing is very similar to welding. It can be opposite, but it's very similar in terms of the technologies that we have to put in place. Remember that the laser distance between the distance between two consecutive planes is 30 microns. So we have to use very, very special techniques in terms of meshing, finite element modeling, to activate, deactivate the elements where we compute the thermal analysis. Because if we don't do that, one computation will last 20 years. Okay, so we have to take into account this, and this has been done, and we have now computation time, which for the worst case maybe last 10 hours, but for most of the case it's a couple of minutes. Okay, so it's very important to do that.
Okay, thanks. We have a lot of questions. I think it will be possible to attend all those questions. What I propose, if you can send your questions by email to the mail I just sent to you in Spanish or English. Decía que hay tantas preguntas, no podemos contestar a todas. Os invito a mandar vuestras preguntas al email o a vuestro contacto comercial, porque han entrado 30 preguntas de golpe. Lo que propongo es que contestemos uno a uno. ¿Vale? No hay una estoy checando si hay una genérica para todo el mundo. Que pues es complicado, o sea, además viene en castellano, las tengo que traducir a marcha, va a ser complicado, son muy largas. Si estáis de acuerdo, lo dejamos aquí. Este webinar se ha grabado, de tal forma que lo vamos a ver cómo lo podemos publicar de la mejor forma, si lo queréis volver a escuchar, y estamos a vuestra disposición a través de vuestro contacto comercial o el email que os acabo de mandar. Pues espero que la experiencia de webinar ha sido satisfactoria para todos. Gracias a Juan Francisco y Daniel por su intervención. Y
merci de votre attention.
Ok, merci beaucoup.
Bye bye.
Bye.
Thank you. Bye bye.